In this discussion, we're going to focus on the average mass values on the periodic table and how those are derived. Okay, isotopes are atoms of the same element, so their atomic number, or Z as it's shown here, is the same, but they have different number of neutrons in the nucleus. So this is one of the developments that changed part of Dalton's theory. Dalton said that all atoms of a given element are identical. Well, he didn't know about neutrons, and so we can have atoms of the same element, that's based on the number of protons, but they can have different number of neutrons, which is just going to change the mass of the atom. And so this is the format that we'll use in designating specific isotopes. And so you'll see we have the atomic number of protons is down in the lower left. We have the atomic mass in the upper left. And then if it has a charge, we'll still put that on the upper right as we did before. Here's an example of a neutral atom of hydrogen. It's hydrogen because it has one proton, and in this case, since our mass number is 1, we have no neutrons present, and since it's neutral, protons and electrons are the same. So again, to compare the isotope, or our mass number, is a function of protons and neutrons, whereas the charge is a function of looking at protons versus electrons. Alright, here is an isotope of sodium that is also an ion, and so it is sodium because it has 11 electrons. Its mass number is 23, so 23 minus 11, it has 12 neutrons. And then because it has a +1 charge, that means it has one more proton than it does electrons. So it has a charge of +1, it has 10 electrons. Here's another example. Here it's cesium because of the atomic number being 55. Okay, it has 133 minus 55 gives us 78 neutrons in the nucleus. Okay, in this unit we're going to be focusing on mass of elements, mass of compounds, but we're looking at it from two perspectives. And when we're talking about atoms and molecules, the unit of a gram is really not very convenient, mainly because they're so small that we would always be having to write exponential form for our masses if we reflect the masses in grams. And so what we have is we have another mass scale, another unit that we use when we're talking about atoms and molecules, and this unit is the atomic mass unit, or AMU. The way these values were developed for each element was they started off and just defined the carbon-12 isotope as equal to exactly 12 atomic mass units. That's the basis for the relative mass scale. And then to get the masses of any other isotope, they just ratioed it based on its relative mass compared to carbon-12. So if you had an isotope that was 2 times the mass of carbon-12 in grams, then it would also be 2 times the mass of carbon-12 in AMUs, or 24 AMUs. So the relative values of the masses do not change. It's just that the actual value in AMUs is more convenient to use than if we were using grams. Okay, so how do we get the average masses on the periodic table? All right, these average mass numbers are typically not whole numbers. And so that's one thing to make sure, is that you have it clear in your mind that the mass number and the average mass are not the same. Mass number is always going to be a whole number. It's protons plus neutrons. But this average mass that you see on the periodic table, that is a weighted average of all of the naturally occurring isotopes of an element. So let's look. Here our example is lithium. And what this says is that if I have a large sample of lithium, that 7.42% of them would be the lithium-6 isotope, and 92.58% of them would be the lithium-7 isotope. So if we're looking at what the average mass is of lithium, we would expect, since a lot more of them are lithium-7, we would expect the average mass of lithium to be closer to 7 than it is to 6. Okay, so we do a weighted average. You take the percent times the mass plus the percent times the mass of however many isotopes you have. In this case there's 2. Divide that by 100 and we get an average mass of 6.941 atomic mass units. So it's a weighted average. Now how do we come up with those percents? Okay, we do that with the mass spectrometer, and you should be at this point a little familiar with how that works, and we're going to kind of take you all the way through the process at this, because the end data that we get if we're analyzing elements with a mass spectrometer is the percent abundance. So here's our general picture, okay, and let's take it one step at a time. They go into the mass spectrometer in gaseous form. The ion source contains an electron gun, something that's generating high energy electrons. They knock electrons off of the particles, these atoms that we are in our sample, and give them a positive charge. Okay, these are then accelerated by an electric field. We want to pull them out of the ion source, make them move forward. Okay, so again, since they're charged particles, they will respond to an electric field. And then their path is deflected. We make them turn, either using a magnetic field or an electric field. We cause them to turn. And what happens then is that the particles eventually will hit a detector, and the detector is set up to where it can count how many particles hit the detector in a certain location. Well, what does this have to do with the isotopes? Well, when they undergo that deflection, the heavier the isotope is, the less its path will be deflected. And so what you can see is it essentially separates these particles by mass, okay, hence the name mass spectrometer, okay, and so we would see at the least deflected position, we're going to see the heavier isotopes, and at the most deflected position, we'll see the lighter isotopes. So what do we get out of this? Well, we get something that looks like this. Okay, we're just going to be focusing in on where all the particles have a charge of +1 for what we're doing. And so you're going to see this is a mass spectrum here. And let's take a little closer look at this. This is more like what it would look like coming out of our mass spectrometer. And here for neon, if we look, this says that 90.92% of the neon atoms that hit the detector were the lightest isotope, neon 20, whereas 8.82% of them were the heaviest isotope, the neon 22. And so this is what I want you to be able to calculate an average mass from, is one that looks just like this, where you have on the x-axis, that shows you the mass, it gives you the mass of the isotope, here, here, and here. And then the height of the peak, that's what gives you the abundance. So here again, we use the same type of calculation, as you can see, to find the atomic mass. Okay, here it's giving us potassium, and this is a little bit different type of problem here. It says we have 2 isotopes, And we want the percentage of each isotope present if our average is 39.1. So this problem is giving us the average. That's our average mass. And it's wanting the percent abundance. Well, if there's only two of them, if the percent of one is X, the other one has to be 100 minus X. They have to total 100 if there's only two of them. So basically you're just going to plug that in, set up the equation the same way, solve for X, and then our final answer would be that the potassium 39 is 95%, potassium 41 is 5%. Okay, so here, what's our relative atomic mass for this element here? Okay, and it's telling us that this value here, that line is at 38. Okay, and the other line is at 40. All right, so take a minute, calculate this. You can pause this if you need to. And we'll go on to the next to see if you got it right. Okay, although we won't be discussing it in this unit, and this is the subject for chemistry study in college, they do use mass spectrometers to analyze molecules. And I just wanted to kind of show you in general what this is, that we don't just use these for atoms. Basically, you can make ions out of molecules as well. Again, all it means is it has a charge. It goes through the same process as they do with the atoms, and the same type of analysis in that the amount of deflection is based on the mass of what would be the fragment, because typically we're breaking the molecules apart when they enter the ion source. And what they do is they use the masses of the fragments and the way that they break apart to determine what the substance is. And so again, your output looks very similar. It's just a little more complex than what you see with elements, because you've got pieces of molecules and how they break apart, and you would have lines on your mass spectrum for each of these fragments. But the thing is that they experiment with knowns, and so they have a big library of what the mass spectrum for different molecules looks like. And then they use that to analyze unknown substances.